Although the normal distribution can be used to solve many problems in engineering and science, there are still numerous situations that require different types of density functions. Two such density functions, the gamma and the exponential, are covered in this lesson. It turns out that the exponential distribution is actually a special case of the gamma. Both find a large number of applications. The exponential and gamma play an important role in both queuing theory and reliability problems. So time between arrivals and service facilities and time to failure of component parts or electrical components are nicely modeled by the exponential distribution. The relationship between the gamma and exponential allows the gamma to be used in similar types of problems. The gamma distribution derives its name from the well-known gamma function, studied in many areas of mathematics. Graphs of several gamma distributions are shown in this figure. The special distribution for which alpha is equal to 1 is called the exponential distribution, and that would be this curve. And I'll highlight that in purple. But alpha is equal to shape and beta is the rate. Those are two parameters of the gamma distributions. But that highlights the exponential distribution. The continuous random variable x has an exponential distribution with parameter beta if the density function is given by f of x with beta is equal to 1 over beta e to the minus x over beta for x greater than 0 and at 0 elsewhere. The mean and the variance of the gamma distributions are mu is equal to beta and variance is equal to beta squared. The most important applications of the exponential distribution are situations where the Poisson process applies. Recall that the Poisson distribution is used to compute the probability of specific numbers of events during a particular period of time or span of space. In many applications, the time period or span of space is the random variable. So for an example, an industrial engineer may be interested in modeling the time t between arrivals at a congested intersection during rush hour. An arrival represents the Poisson event. Time t between arrivals represents exponential. So the time between the arrivals would actually be the exponential event. In Chapter 5, the Poisson distribution was developed as a single parameter distribution with parameter lambda, where lambda may be interpreted as the mean number of events per unit of time. Consider now the random variable described by the time required for the first event to occur. Using the Poisson distribution, we find the probability of no events occurring in the span up to time t would be given by the probability of 0 events occurring, lambda t, is equal to e to the minus lambda t times lambda t to the 0 over 0 factorial, and that equals e to the minus lambda t. We can now make use of this and let x be the time to the first Poisson event. The probability that the length of time until the first event will exceed x is the same as the probability that no Poisson events will occur in x. The latter, of course, is given by e to the minus lambda x. So as a result, the probability that x is greater than little x is equal to e to the minus lambda t. Thus, the cumulative distribution function for x would be given by the probability that x is between 0 and little x would be equal to 1 minus e to the minus lambda t. And that is the cumulative distribution. The density function for the exponential distribution would be f of x is equal to lambda times e to the minus lambda t, which is the density function of the exponential distribution with mu equal to 1 over lambda. From Chapter 5, you should recall it is often said that the Poisson distribution has no memory, implying that occurrences in successive time periods are independent. The important parameter 1 over lambda is the mean time between events. In reliability theory, where equipment failure often conforms to this Poisson process, 1 over lambda is referred to as mean time between failures. Many equipment breakdowns do follow the Poisson process, thus the exponential distribution does apply. Other applications include survival times in biomedical experiments and computer response time. Okay, let's look at this example. Suppose that a system contains a certain type of component whose time in years to failure is given by big T. The random variable t is modeled nicely by the exponential distribution with mean time to failure, beta, is equal to 5. If 5 of these components are installed in different systems, what is the probability that at least 2 are still functioning at the end of 8 years? So the first thing we want to do is we want to find the probability that t is greater than 8 is equal to lambda, and lambda would be equal to since mu is equal to 1 over lambda and beta is equal to mu, then lambda is equal to 1 over mu, or 1 over beta. So we would have 1/5, so we're going to integrate from 8 years to infinity of lambda, which is 1 over beta, so that would be 1/5 times e to the minus lambda t, which is 1/5 times t dt. So when we do this integration, this would equal e to the minus 8 over 5, which is approximately 0.20. So now we have the probability that a given component is still functioning after 8 years is 0.20. So 0.20 is the probability that a given component is functioning after 8 years. Now we want to let x represent the number of components functioning after 8 years. We're going to use the binomial distribution, so we'll have the probability that x is greater than or equal to 2 is equal to x is equal to 2 to 5, because we have 5 components. Of success is 0.20. So if you remember, when using our binomial tables, in order to get greater than 2 or more, it is 1 minus r minus 1, so it would be equal to 1 minus the sum of x equals 0 to 1. So we go to that, and we find that that value is 0.7373. So the probability, and we subtract that from 1, and so then the probability that 2 are still functioning, that at least 2 are still functioning at the end of 8 years, is 0.2627, based on the binomial table of probability that x is greater than or equal to 2, and we had 5 components, so we went from x is equal to 2 to 5, probability of success at 0.20, and when we have at least, we do 1 minus r minus 1, and we come up with 1 minus 0.7373, or 0.2627, probability that 2 are still functioning at the end of 8 years.